So I'd like to introduce both David Blair, who's a Senior Vice President with our firm, GEM Energy, as well as Steve Gillette, who's an executive who runs the Applications Engineering Department at Capstone Turbine Corporation, the manufacturer of the gas turbine engines that are used in all of our installations across Toledo. So if you gentlemen would join me up here, we'll start your presentation.
For me to stand in one spot is probably impossible, but I'll do what I can here. There's two portions here to the presentation with the title, Advanced Turbine Power. The first part, I'm going to cover the opportunity, why you want to be doing this, and what is combined heat and power. And then from here, we will move on to Steve Gillette will focus closer in on the Capstone turbine technology, which is a key ingredient in this solution. We look at a mission-critical structure, data center being the topic of conversation, but it could also be a communications center, it could be a control tower at an airport. The most important item is to maximize reliability. Because a data center is a business, there's uptime and throughput requirements to maintain the flow of data. We like to talk about the cloud. It's an interesting concept, but in reality, the cloud is brick and mortar somewhere. And that brick and mortar has to be functioning all the time. It cannot go down. There's an energy associated with doing that. And as we've pointed out in several presentations very clearly today, the energy in data centers is growing rather than going down, even though the technology is actually driving down the efficiency, the energy consumption of the individual transistor. The data center has been also clearly presented in other presentations, represents the actual calculation of data is only 50% of that energy. The rest is going into cooling and infrastructure, pumps and devices in the building. We want to plug that data center into our power system. Here in the United States, we enjoy a power system that's been developed over a span of 100 years, roughly. The idea was to construct ever larger power plants using the principle of economy of scale, and therefore making them more and more efficient by making them very, very large. And therefore, they're far too big to run a data center. And so then we have to build a transmission system to connect those power plants to the data center. We look at that electric grid. In general terms, it's okay, but in the terms of a data center, it's just not reliable enough. So now we have to have all kinds of band-aids, belts, and suspenders around that data center to make it work. Our grid is vulnerable. We just had an example of Sandy marching through New York City. But there's other things that can go on. And the most, along with that is, terrorist attack, which we've become too well acquainted with. Earthquakes. That storm could also be expanded to the impact of sunspot activity. We know that our grid is vulnerable to sunspots. So the net effect is we've got to have backup solutions. Traditionally, large diesel generators sitting on the site, huge investment in iron and equipment that does nothing but wait for the power outage. And when it does come, there remains some risk as to whether that system is actually going to operate. we give up efficiency in order to get there. And we've seen several different presentations of what's happening there. And the worst thing is we've built this enormous power plant that's 100 miles away, and we're throwing away 2/3 of the energy that's going into that power plant because we can't bring it to the point of use. Given the fact that we've got a world supply of energy that's decreasing, in terms of fundamental resources, we need to be better stewards of our environment, but also better stewards of our diminishing resources. As an engineer, this is an exciting opportunity. How can I go after that missing link? So let's consider moving the power plant to the point of use, putting it right next to the data center. And we heard a little discussion about Syracuse University. In the tours today, you're going to see many examples, at least 6, that will show you how power plant has been brought to the point of use and how this is possible with today's technology. It's not an experiment. We've been doing this for over 10 years, and it's a reality and not a concept. Combined heat and power, or cogen, has the potential very quickly to generate 80% efficiency calculations of the input fuel. Higher levels of efficiencies are also possible, but 80% is a very easy, achievable norm. And that's compared to a traditional system where your electricity is in the neighborhood of 33% efficient, and then you're trying to come up with both a chilled water capacity using the electricity, and you're also trying to heat your facilities using on-site fuel. Very quickly, using available technologies, there's 2 methods, the gas turbine or the reciprocating engine. The reciprocating engine possibly has a 100-year head start on the gas turbine. But in my recent air travel, there were not reciprocating engines on the wing of the airplane. There were gas turbines, and there's a reason for that. And we took a close look at what were our possibilities here as we were presented with these projects. Compare the gas turbine to the reciprocating engine. The gas turbine has a high level of reliability, has a fewer number of moving parts, less maintenance, and the heat recovery, or the way to recover energy from the exhaust stream, is very simple because you're only working with one venue. You're working with an exhaust stream that's largely hot air, and that hot air, the exhaust stream has a specific gravity that makes it look like hot air. So it's a very simple medium to work with from a heat recovery standpoint, so you can transfer that energy into some other use very quickly, very simply. Reciprocating engine, on the other hand, you've got multiple methods that you've got to go after. You've got not only the exhaust stream, which can be highly corrosive, but you've also got cooling water jackets, and then you've got a lubricating oil stream. So you've got 3 different complex methods that have to be employed in order to get at heat recovery. And then you've got the question of emissions. The gas turbine is much more environmentally friendly, and we'll give you more information about that. The reciprocating engine has got to have additional features and tools added to it to clean up that exhaust stream. Using our gas turbine engine, we've got an electric production, but we also have an exhaust stream, and we can take that exhaust stream and take it directly to an absorption chiller and use that absorption chiller to produce cooling water and do that with typically 80% or better efficiencies. Again, everything you see here is proven technology, not an experiment. The proof of the discussion is the Syracuse Green Data Center. It was a collaboration of an outstanding team comprised of Syracuse University, IBM, and we were honored to be a part of that. GEM was selected to participate because of our experience going back 10 years in developing and deploying combined heat and power systems, such as were envisioned for Syracuse. The rest of the story was we were asked and encouraged to think outside the box. If an invention was needed, let's go after that and find out what it would take to bring that invention into reality. And oh, by the way, the groundbreaking is going to be in May, and we want to be online in December. So you've got 6 months to come up with something that's never been done before. The good news is we were up to that task. The system, as you have seen in these other presentations, was composed of 3 components. We were generating electricity with the Capstone turbines, but we were also making cooling water for the data center, and then we were also making hot water, which was going into the adjacent classroom facility. We go back and look at that equation of how the energy is used in a mission-critical application. If I generate the electricity on site and I use the exhaust stream to make the cooling, I no longer have to run a chiller that's electrically driven. So I can remove the 27% from that equation. I'm using the generator now and using the exhaust energy. So now I've quickly changed my PUE calculation to 1.46, and I'm only getting started because now I can go after the other supporting infrastructure in there, and some of the ways we could do that is by going after how cooling water is taken to the servers. And Roger Schmidt talked about the rear door cooling. That impacts this PUE. And then another thing we can do is we've got redundancy in this system, and that redundancy, rather than being idle, can be used productively. So in other words, if 4 out of 5 generators are used to run the data center, and we could operate the remaining generator and send that electricity somewhere else, and so then we use some of our redundancy. Yet, if the non-critical load becomes expendable and the data center becomes the priority, so now our reliability is very high, but our opportunity to recover energy is still there. So this PUE can be driven even lower by looking at more and more of the details. From here, I'd like to move on to Capstone.
Great. Thanks very much, Sam. I appreciate the opportunity to be here, and Bill and Hussein and Dave and the rest of the folks at GEM and GEM BHP is what it is now. GEM Energy. GEM Energy. Okay, thanks again. So I'm going to focus on the microturbine portion of this, and I have to start because Capstone is a public corporation. I always have to put a slide in here which I call the Anti-Miranda Act. All that says is that anything I say today cannot be used against me in a court of law. So I'm simply going to talk a bit about Capstone, the microturbine, of course. We have a unique variant of the microturbine that I'll explain that's been used at Syracuse, and you'll see here later today at the University of Toledo installation. I do want to talk a little bit about availability and reliability and some of the benefits of this technology. And just again, touch back on Syracuse University. That's obviously our first site, and we're very proud of that. And we have a couple of folks from Syracuse University here as well, and appreciate you coming down. If you've got some questions, you'll obviously be seeing hardware today, but you can also get some operating experience from the guys from Syracuse that could be very useful for you. So what's a microturbine? Really just a small gas turbine. We've done it in a little bit unique way in that we've got the generator and the very simple compressor wheel, turbine wheel, all on one shaft. One moving part, we like to say, and that's all supported on air bearings. So you don't have to change the oil, you don't have to dispose of the oil, so it helps with the maintenance and also the emissions benefit of the technology. But one thing we've added is something we call a recuperator. And what that does, like an intercooler, if you've got a turbocharged engine in your car, it actually exchanges the heat energy from the exhaust and preheats the air coming into the turbine so that you have to use less fuel, therefore you have a higher net electrical efficiency. And that's unique to microturbines in the size that we're in. So that's basically the power plant, very simply. But what comes out of this system, we're spinning at a very high speed. In the case of the 65 kilowatt microturbines, that's 96,000 RPM. So we're really spinning very, very fast. So what comes out of this generator is high frequency AC. And so what we do is we take advantage of state-of-the-art power electronics, the same power electronics that are used in a UPS system today, or a variable frequency drive. And so we'll take that high frequency AC that's coming out of the turbo generator assembly, and we'll rectify it to DC. So we got an internal DC bus here that we converted the high power, high frequency to DC. And then to connect to the grid out here, we've got another module, an inverter, same kinds of power electronics, to take the DC and convert it to 50 hertz or 60 hertz AC that'll be used in the facility. And then we also have a version that has a battery backup for starting. So if you're standalone, you didn't have any grid at all, you need to have some energy to start the system. So we take that from a battery through another converter, in this case DC to DC, allow us to provide power to start the turbine. And also we use that kind of to level load. Turbines don't like to change very rapidly the power output. So we use the battery as a source and sink to make sure that the output on the utility side over here, the user side, remains very stable in terms of frequency and voltage. So that's our basic microturbine. We started producing them in 1999. And that's the mainstay of our business, stationary, power generation, both standalone like I'm showing you here, or just simply connected to the grid. But what we realized when we had this opportunity with IBM and with Syracuse University and with GEM is that we had the makings of another product. And so what we realized is that the traditional way of protecting, as Dave was talking about here, you've got to have some redundancy in your system to deal with the fact that the utility grid isn't always going to be available, so you've got to have some backup. And traditionally that backup is a double conversion UPS system, a backup generator. The UPS system is for kind of short outages, maybe 10, 15 minutes, maybe half an hour, maybe an hour, depending on the battery bank, but a relatively short period of time. Then for longer periods, you've got a backup diesel generator, typically someplace, that can go for extended outages. And then if you want to get the economic benefits of cogeneration that we've been talking about, then you'd need a separate cogen system. So what our system does actually combines all three of those into what we call the hybrid UPS microturbine solution. So how does that work? So you remember the picture before? I showed you we've got a power electronics module. We call it a load control module. It's able to take our DC bus and make it available as power to AC load out here. We got our turbine generator with its module here to get from the high frequency AC to the DC, and we've got another DC to DC module that'll get you down here to a battery. We said we got all the pieces, we just add one more of these load control modules, connect it to the utility source, and now we have what we call our hybrid UPS system. And it can work in 3 ways. The first way is it works just as a double conversion UPS system. It is a double conversion UPS system because we can take power from the utility, rectify it to DC, invert it back to the critical load. That's exactly what a UPS system in every data center today is doing. So we've got that functionality. So we can be connected to the grid when it makes sense to get your power from the grid. But we also have another way we can work this system, what we call high efficiency mode. And it's very flexible because we can turn on any of those generators, and Dave kind of alluded to this, right? In the case of the Syracuse system, we've got 12 generators, 6 on each side. We can run whatever number of microturbines makes sense to run given the thermal load and given the electrical load that's in the facility. You've got complete flexibility of whether you want to generate just enough power for the critical loads, or maybe a little less and pull some in from the utility, or maybe a little more and push it out and use it up in an adjacent building. So very flexible, and you can maximize the efficiency and therefore the economics of running the system. And then of course, if for some reason the utility goes away, we're providing the backup. If the microturbine isn't already running, we'll take some energy out of the battery, start the turbine. In the meantime, the battery also can provide power to the critical loads, so there is no interruption of power under any of these scenarios to the critical load. So we've got a high reliability, high availability, high efficiency solution. So just some examples. Dr. Khalifa did some examples here comparing different areas of the U.S. This is just an average, taking the average U.S. power plant. But it shows you the benefit of using this technology in terms of reducing CO2, in terms of criteria pollutants, NOx, very important for air pollution. In terms of the energy, the fuel that was talked about by Dr. Hirsch. We want to reduce the amount of energy, the amount of fuel at the end of the day that it requires. We can make a significant reduction there. And of course, you can express all of this in terms of equivalent cars removed or whatever. The other thing that's, of course, very critical, so this is a good technology solution, very efficient, can be economical. We'll talk about that in a minute. But it's not going to go anyplace unless the CIO, who's got responsibility for the data center, says it's going to also meet the reliability challenges that he has. So this is simply a chart. I won't go through all the math, but it demonstrates that we can, in fact, get to the 8 nines of availability that is expected in a good Tier 3, Tier 4 data center. So here's the chart I like the best. It's very simple. It's actually at the essence of what, again, Dr. Khalifa was talking about earlier. So you got an alternative when you're putting a data center together. You certainly need backup. You need some kind of way to protect in case of a utility outage. And so the traditional way, this example, I'm just making a relative comparison here. So you spend some capital for a UPS system and a backup generator. And they're there for a purpose, and they serve their purpose, and they've done well. There's no problem with them actually doing, for the most part, the very function you've bought them for. But once you spent that capital, putting electricity through the UPS system, there's some efficiency loss. So you're going to pay some extra kilowatt-hour charges every minute you're running the UPS system. Plus, you got to pay maintenance for the UPS system. You got to run the backup diesel generator once in a while. You got to pay maintenance for the diesel generator. So the return, direct return on that capital investment is negative, and it's every year you're operating it, you're getting deeper into the hole. So compare that with taking our hybrid UPS system. It's a little more expensive, a little more technology in there, more equipment, but depending upon the electric rates and gas rates and how, what your facility is like, you have the opportunity to save money, save on your utility bills over time, and so you can pay back this investment. And so it's interesting here, right? The investment, if it was just looking at this capital and getting a savings, and in this example, a 4-year payback, compared to the losses that you had doing it the other way, you got a 2-year payback. So it makes a lot of economic sense to consider this kind of technology when you're looking at your solutions for your data centers. And of course, here's a bunch of advantages that we could go through about why the technology is better than the traditional way. We've talked about the economics and some of the other things like UPS systems actually have to go inside. So you're taking up valuable indoor space in a traditional way where we can actually go outside. A few other things that I think these presentations will be made available to everybody, is that right?
Absolutely, yes.
So you can always study this later if you want to, but the bottom line is this is a very economic way to deal with your problems. And you've heard a lot about Syracuse Data Center, the objectives of getting 50% less energy usage than a typical facility. And I don't think Dr. Khalifa said it directly, but maybe you could say, what percentage of this 50% that you're trying to achieve came from the CHP or the cogen solution? I would say it's probably the majority of that, right?
It's true, most of it.
And the other thing I wanted to mention, I won't go through the project itself, but Syracuse University has been very, very open. They've had visitors from around the world come through the facility. We've got sort of our Hollywood star back here, Mark Weldon. You can actually go to their website. They're very proud of this. They've got some videos on there that will explain not only the microturbine operation, but a lot of the other things that they did to improve the efficiency in the operation at their data center. So I would encourage you to, when you have a minute, go to the Syracuse University website and listen to Mark explain all this technology. And then the last thing is, if you want to know more about Capstone, we've got our website, microturbine.com or capstone-turbine.com. And of course, you've got right here hosting us is our distributor for this territory, Gem Energy. So you got all the right folks in the room today. Please take advantage of it. Ask as many questions as you can think of. I'm here. Sumner Bachman over there in the corner from Capstone is here. You've got a lot of folks from Gem Energy that can answer your questions, as well as folks from Syracuse University. So again, thanks for the opportunity to talk with you today.